Hello everyone. This lecture is exclusively recorded for final year BSc Mathematics student of BK Birla College, Kalyan. This is Mathematics paper 1. In this paper or in this lecture we will study second fundamental theorem of calculus for line integral. So let me state the theorem statement. Let capital U, which is subset of Rn, be an open connected set. F from U subset of Rn to R is differentiable scalar field with a continuous gradient grad f on an open connected so on U subset of Rn. Well, this grad f means I hope we all are knowing what is grad. So it is dou by dou x1 comma dou by dou x2 dot dou by dou xn. So I'll write that little later. So then for any 2 points A and B in U connected by a piecewise smooth path capital C in U, then line integral of over C gradient f dot d alpha is equal to f of alpha b minus f of alpha a, where alpha is a function from closed interval a comma b to u subset of okay. So let me write down alpha on the next slide, where alpha is a function from closed interval a comma b to u subset of Rn. Right. So what is alpha? Alpha is a parametrization of curve C. Is a parametrization. for C. Okay, so before proving this, let me just recall what is gradient and all. So recall. So see, grade is basically dou by dou x1, comma dou by dou x2, comma dot 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 dou by dou xn. So it is a vector quantity, and gradient f will be, if f is a scalar field, f has to be scalar field, then only grade f is defined, dou f upon dou x1, comma dou f upon dou x2, comma dot 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 dou f upon dou xn, if it is n vectored in Rn. Right, so this, I hope you all remembered this, or we all aware of this, because we have done this in the second year of BSc. So let's go for the proof. So we choose 2 points A and B in capital U, and you know that U is open and connected, because this initial hypothesis, this is an assumption, U must be open and connected. So there are 2 cases. So case 1 is the 2 points in A and B are connected by smooth path in C, right? So so the 2 points A and B are connected by smooth path by C. So the smooth path is called as a C. So let alpha be a parameterization for C. So alpha from closed interval A comma B, which is subset of U in Rn. So note that U is a subset of Rn and C is a curve inside U. So be a parameterization of C. So then the line integral along C, gradient f d alpha, as per the definition of line integral. Note that f is a scalar, but grad f is a vector. So basically we are finding the line integral of a vector field. So as per the definition of line integral of a vector field, it is line integral from A to B, gradient f evaluated at alpha t dot product with alpha dash t dt. So let's call this as 1, and we must write down here, this we could write only because by definition of line integral of vector field. Okay. Now we will be defining one more variable called as an phi, define phi, which is a function from closed interval A comma B to Rn, defined by so such that phi of t is equal to f composed with alpha of t. Now let's see whether this composition is possible or not. So we know my f is a function from u subset of Rn to R, and alpha is a function from closed interval a comma b to u subset of Rn. So this is alpha. So then I'm defining a phi which is equal to, while taking composition we supposed to write down f composed with alpha, f composed with alpha t. So that is also phi. So then I need to write down here phi of t, or we can say phi is equal to f composed with alpha. So this composition is well defined and it is possible. So phi is equal to f basically. So it is given that or maybe f is differentiable, alpha is differentiable because it is a smooth parameterization for C, and being a parameterization it has to be differentiable. So f is differentiable, alpha is differentiable. So the composition of two differentiable function is differentiable. That would imply the phi, the function phi is differentiable. So let us write down this. Since f and alpha are differentiable, this would imply f composed with alpha is differentiable. This would imply f composed alpha is basically phi. Phi is differentiable. So it's differentiable on domain. So domain of a phi is closed interval a comma b. So it's differentiable on closed interval a comma b. So if it is differentiable, then I can definitely find out the derivative of this. So what will be the phi dash t? So it is basically I need to use the chain rule over here. So you please remember this. It is phi of t is f of alpha t. So it is f of alpha t, but f is basically how does it looks? So it has well, it is a scalar field, that's true, but then f of alpha t, how does it looks? So let me write down this somewhere this side. So f of alpha t, so alpha is a vector. So suppose alpha is x1t comma x2t comma dot 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 xnt. So f look like this way. So it has x1t comma x2t comma dot 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 xnt. And somebody asked me to find out the derivative of this, then it will be like this. So what will be the derivative of this? It will be d by dt of f of alpha t will be, it is dou f upon dou x1 into dx1 by dt plus dou f upon dou x2 into dx2 by dt dot 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 dou f upon dou xn into dx by dt. And you can see that this is equivalent to saying that it is dot product of dou f upon dou x1 comma dou f upon dou x2 dot dou f upon dou xn dot product with dx1 by dt, or I can say x1 dash t x2 dash t, that will also work out. x1 dash t x2 dash t dot xn dash t, and which is same as gradient f dot product with, this is basically alpha dash, so alpha dash t, right? So, and I could write this only because this is basically a chain rule, one should know this is chain rule. So here, so phi dash t will be, here it will be gradient of see, so what is phi? Phi is f of alpha t, and basically it is d by dt of f of alpha t, which is equal to, just now we have seen, it is gradient of f of, so f is defined at alpha t, so one that is understood. Here I did not write here f of alpha t, but it is understood f is defined at alpha t dot product with alpha dash t. Okay, so let's call this as 2. I have defined 1, I have defined 2, and here the reason one should write down by chain rule. So this right hand part which I have explained here, that is, you in exam whether you write it or it's up to you. Writing this will be fine. If you feel that no, you can understand, you have understood directly, you may write this step straight away, that is not an issue. So then let us find out the LHS of my given expression. I need to show that, what is my aim? My aim is to show that line integral of gradient f is equal to f of alpha b minus alpha a. So let's start with the left hand side, like that is line integral along C, gradient of f. So consider line integral of C gradient f dot d alpha, which is same as, what is gradient f? We have seen that my gradient f is same as my phi dash. So it is equivalent to saying that I need to find out line integral from, or maybe just wait. So this is same as line integral a to b gradient f alpha t dot alpha dash t dt, right, from 1, because 1 we have said this only. You can go to 1 and you can check. Yeah. But this grad f of alpha t dot alpha dash t is basically phi dash from 2 a to b, that is phi dash t dt. So from 2. Now see, what I know about the phi is as follows. Where is phi? Yeah, see, f is continuously differentiable, alpha is also continuously differentiable, f composite alpha is phi, which is also continuously differentiable. When I say continuously differentiable, that means phi is differentiable and the derivative of phi is continuous, so then it is called as a continuously differentiable. I again repeat, when I say phi is continuously differentiable, That means phi is differentiable and the derivative of phi is continuous. Maybe if I have not mentioned that f is continuously differentiable, we will write down that at beginning here is continuously differentiable scalar field. And the parameterization alpha is already continuously differentiable. That's a definition of parameterization. So here we know that phi dash is continuous and it's a scalar field. Is it mentioned? I have already given. Yeah. No, it's a vector field. Phi is a function from closed interval a comma b to, that's a mistake I did. It's a function from closed interval a comma b to r. Please note this. So phi is a scalar field. So this implies this is same as phi of b minus phi of a. Why I could write this? Because phi dash is continuous on closed interval a comma b. So if it is continuous, it is R integrable because it is bounded. So by second fundamental theorem of integral calculus, we can write down this phi of b minus phi of a. So by second fundamental theorem of integral calculus. So in semester 3 we have studied the Riemann integration and all, and in that we had a second fundamental theorem of integral calculus. So this is basically a primitive phi dash. So it says that the line integration from a to b phi dash t dt is phi of b minus phi of a. But what is phi of b? I already know what is phi of t. Phi of t is basically f of alpha t. So phi of b is f of alpha b and phi of a is f of alpha a. So this is same as f of alpha b minus f of alpha a. And it is what we need to prove because it is mentioned that show that line integral of over c gradient of f is f of alpha b minus f of alpha a. This was case 1. Now the case 2. Now we assume that it is a and b are connected with a smooth curve. Now we will assume that a and b are connected with the piecewise smooth curve. So the path is not direct. So there are c consists of c1, c2, c3 and some finite uh, like uh, suppose this is my a to b straight away. Now I'm saying that a and b are connected with some smooth curve like this is. So there are different it is consist of, so let me call this as c1, this is c2, this is c3, this is c4. So c is c1 union c2 union c3 union c4, so on and so forth. So that way. So case 2, let a and b are connected by piecewise smooth path C. So let C be a piecewise smooth path so we divide the interval a comma b into subinterval xk minus 1 comma xk, where k goes from 1 to n. This implies the line integral along C gradient f d alpha is equal to integration a to b gradient f of alpha t dot product with alpha dash t dt. So now since it is piecewise smooth, so like I said, it is C1, we will find out C1, then C2, C3, and then we will add it. So it's a equivalent to saying that summation k goes from 1 to n, line integral over xk minus 1 to xk gradient of f of alpha t dot product with alpha dash t dt. This is same as summation k goes from 1 to n. Now for this line integral we already know, because in case 1 we have proved that it is basically f of evaluated at endpoint. So f at alpha xk minus f at alpha xk minus 1 from case 1. And if I expand this, what I'll get, this is a telescopic sum, so alternate terms will get cancelled. I will only end with the last term and first term. So it will be f of alpha xn minus f of alpha x0. But xn is b and x0 is a, because while doing the partition, we had remembered that the first point is x0 and the last point is xn. So it is f of alpha b minus f of alpha a. So we have observed that in both the cases, so from case 1 and 2, we can write down that the line integral along C gradient f dot d alpha is same as f of alpha b minus f of alpha a. So this completes the second fundamental theorem of integral calculus for line integral, second fundamental theorem of for the line integral. On the same line, we will be proving the first fundamental theorem also. So in next lecture, we will have first fundamental theorem for line integral. Thank you.